Look at the ceiling. Just for a second, look up. Now let me ask you something that sounds so stupid you'll wonder why you're still sitting here. How do you know the ceiling isn't moving? You look at it, it seems still. You look away, you look back, same ceiling, same distance. Fine, but what if I told you that the ceiling is getting farther away from you right now? Not because someone's jacking up the building, not because you're shrinking, but because the space between you and that ceiling, the actual nothingness between here and there, is getting bigger. You'd say I'm out of my mind. And 100 years ago, the smartest people who ever lived would have agreed with you. So let's start even simpler. Forget the ceiling. Let me ask you about a ball. You throw a ball straight up. What happens? It goes up, it slows down, it stops, it comes back. Every kid knows this. Gravity pulls it back. Good. Now throw it harder. It goes higher, takes longer to come back, but it does come back. Throw it even harder. Same thing. Higher arc, longer trip, but always back down. There's a comfortable certainty to that, isn't there? What goes up must come down. You've heard it 1,000 times. It feels like a law. It feels permanent. But here's where the trouble starts. What if you could throw that ball hard enough? I mean, really absurdly hard. Is there a speed where the ball goes up and just never comes back? Not because gravity disappears, gravity is still pulling. But the ball is moving so fast that gravity can never quite reel it in. The answer is yes, there is such a speed. For the Earth, it's about 25,000 miles per hour. We call it escape velocity. Above that speed, the ball leaves and never returns. Below it, the ball always falls back. Right at that speed, the ball barely escapes, slowing down forever, approaching zero speed but never quite stopping. Now, you might think this is a cute physics fact and nothing more. It's the escape velocity of the Earth. Great, that's how rockets work. Wonderful, who cares? But I want you to keep that picture in your head. A ball thrown upward, gravity pulling it back, and a critical speed that determines the ball's entire future. Return, escape, or perfect balance. Tuck that away. Because in about 10 minutes, that little picture is going to come back and hit you in a way you do not expect. It's going to describe the fate of everything that exists. Now let's go bigger, much bigger. Forget the ball, forget the Earth. Look at the night sky. On a clear night, away from city lights, you see stars. Thousands of them. They look fixed. The ancient Greeks called them the fixed stars, and for good reason. Night after night, year after year, century after century, the pattern doesn't change. Orion is always Orion. The Big Dipper is always the Big Dipper. The sky looks permanent and still. For most of human history, that stillness was considered a basic feature of the universe. The universe just sits there. Stars hang in space. Maybe they move a little, orbit a little, drift a little. But the overall picture? Static, unchanging, eternal. Even Isaac Newton thought so. He imagined an infinite, eternal universe with matter sprinkled roughly evenly throughout, and the whole thing just existing forever, unchanging in the large. He did notice a problem. If gravity is always attractive and matter is everywhere, then everything should be pulling on everything else and the whole work should collapse inward. He argued that if the universe were truly infinite, and the matter were spread evenly enough, the gravitational pulls from all directions would cancel out and things would stay put. It was a shaky argument. It's actually wrong, technically unstable, but it held for 200 years because nobody had a better idea and nobody had any evidence to the contrary. Then along comes Einstein. In 1915, he publishes his general theory of relativity. This is the theory that tells us gravity isn't really a force in the old Newtonian sense. It's the curvature of space-time caused by mass and energy. Massive objects warp the geometry of space and time around them, and other objects follow the curves. That's gravity, beautiful theory. Took him 10 years to work out. And when he applied it to the universe as a whole, when he asked, "What does my theory say about the cosmos?" he got a shock. His equations did not allow for a static universe. The mathematics demanded that the universe must be either expanding or contracting. It could not just sit there. Space itself had to be in motion, getting bigger or getting smaller. Those were the only options. And Einstein, the man who trusted mathematics more than almost anyone who ever lived, looked at that result and said, "No, that can't be right. The universe is obviously static." So he modified his equations. He added an extra term, a little constant, a new number that he called the cosmological constant. And the only purpose of this constant was to act as a kind of anti-gravity. a repulsive force that would exactly balance the attractive pull of all the matter in the universe, holding everything perfectly still. A cosmic kickstand propping up a static universe. Think about that for a moment. But the greatest physicist of the 20th century derived the correct prediction from his own theory, the prediction that the universe must be expanding or contracting, and then he erased it. He deliberately rigged his equations to get the answer he wanted instead of the answer the mathematics was giving him. He later called it the biggest blunder of his life. But hold that thought, because the story of that so-called blunder has a twist at the end that nobody saw coming. Not even Einstein. All right, so Einstein's equations in their pure form say the universe should be moving, but equations on paper don't tell you what the universe is actually doing. For that, you need telescopes, you need data. And in the late 1920s, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory outside Los Angeles with what was at the time the most powerful telescope on the planet, a 100-inch reflecting telescope on top of a mountain, made one of the most important observations in the history of science. Maybe the most important. Hubble was studying what were then called spiral nebulae, fuzzy little patches of light scattered across the sky. There was a heated debate about what they were. Some astronomers thought they were just clouds of gas and dust inside our own galaxy, the Milky Way. Other astronomers, the more daring ones, thought they were entire galaxies in their own right, vast islands of billions of stars lying far, far beyond the edges of our own galaxy. The debate was fierce, and it had been going on for years. Hubble settled it. He used a type of variable star called a Cepheid variable. These are stars that pulse, getting brighter and dimmer in a regular cycle. And the beautiful thing about Cepheids is that the period of their pulsation, how long it takes to go from bright to dim and back again, is directly related to their true intrinsic luminosity. A Cepheid that pulses slowly is genuinely more luminous than one that pulses quickly. So if you can observe the pulsation period, you know how bright the star actually is. And if you compare that to how bright it appears from Earth, you can calculate the distance. Brightness falls off with the square of the distance. A candle twice as far away looks 4 times dimmer. Simple geometry. Hubble found Cepheids in the spiral nebulae. He measured their periods. He calculated their true brightness. He compared it to their apparent brightness. And the distances came out enormous, millions of light years. These fuzzy patches of light were not gas clouds in the Milky Way. They were entire galaxies, each one home to billions of stars lying at staggering distances from us. The universe was suddenly hundreds, thousands of times bigger than anyone had imagined. That alone was revolutionary. But that wasn't the real surprise. The real surprise was what Hubble found when he looked very carefully at the light coming from those galaxies. And this is where I need to explain something about light. When you look at a star or a galaxy, you're seeing the light it emits. Light is a wave. It has a wavelength. Different wavelengths give you different colors. Short wavelengths look blue and violet. Long wavelengths look red and orange. In between, you get green, yellow, the whole visible spectrum. When you pass starlight through a prism or through a more sophisticated instrument called a spectroscope, you spread that light out into its component wavelengths. And in that spectrum, you see something remarkable. Dark lines, thin, dark gaps at very specific wavelengths, where the light has been absorbed. Each chemical element absorbs light at its own unique set of wavelengths. So these absorption lines act like fingerprints. You can look at the spectrum of a distant star and say that pattern is hydrogen, that pattern is calcium, that pattern is sodium. The chemistry of a star a million light years away, read from its fingerprints in the light. Now, here's the crucial idea. If a galaxy is moving away from you, something happens to its light. The wavelengths get stretched, they get longer. And longer wavelengths mean the light shifts toward the red end of the spectrum. We call this redshift. If a galaxy is moving toward you, the wavelengths get compressed and the light shifts toward the blue shift. It's the same principle as the Doppler effect with sound. When an ambulance is coming toward you, the siren sounds high-pitched. The sound waves are compressed. When it's driving away from you, the siren drops in pitch. The sound waves are stretched out. Light does the same thing. A galaxy moving away from you has all its spectral lines shifted to the red. Hubble measured the spectra of dozens of galaxies. He looked at where the absorption lines fell. And what he found was electrifying. Every galaxy he looked at was red-shifted. Not some of them, not most of them, every single one, in every direction. North, south, east, west, up, down, it didn't matter. The entire universe of galaxies was moving away from us. And there was a pattern, not a random scattering of speeds, but a clean, beautiful, linear relationship. The farther away a galaxy was, the faster it was receding. A galaxy twice as far was moving away twice as fast. 3 times as far, 3 times as fast. Double the distance, double the speed. This is Hubble's law, and when you really understand what it means, it changes everything. Stop for a moment and think about what this implies. But everywhere you look, galaxies are flying away from you. And the farther they are, the faster they go. Your first instinct, the natural human instinct, is to think we must be at the center of some big explosion. Everything is rushing away from us. We're at the middle of it all. But that's wrong. And the reason it's wrong is one of the most beautiful ideas in all of cosmology. Imagine you're baking a loaf of raisin bread. A big leavened loaf. You've got your dough and you've pressed raisins into it, scattered randomly throughout. Raisins everywhere. Now you put it in the oven. The dough rises. It expands. Every part of the dough pushes outward uniformly. The raisins don't move through the dough. The dough carries them. Now pick any raisin. Call it your home raisin. Look at the raisins nearest to it. They've moved away a little, because the small amount of dough between you and them has expanded a little. Look at raisins farther away. They've moved away more because there's more dough between you and them, and all that dough has expanded. The farther the raisin, the faster it appears to be receding from you. Exactly Hubble's law. But now, and this is the key, pick a different raisin, any other raisin in the loaf. Stand on that raisin and look around. From that raisin's point of view, the exact same thing is true. Every other raisin is moving away from it. The nearby ones slowly, the distant ones quickly. Every raisin in the loaf sees itself at the center of the expansion. And no raisin is actually at the center because there is no center. The expansion is happening everywhere, uniformly, in the dough itself. That's what's happening to the universe. The galaxies aren't flying through space like shrapnel from a bomb. Space itself is expanding. The fabric of the universe, the actual distance between things, is stretching. The galaxies are the raisins. They're not moving through the dough. The dough is carrying them apart. The expansion isn't happening at some location in space. It's happening to space. This is a genuinely hard idea to hold in your head. We're trained to think of motion as movement through space. A car drives down the road. A bullet flies through the air. Motion means something going from here to there through a pre-existing space that just sits there like a stage. But the expansion of the universe is different. Nothing is moving through space. The space is changing. New space is being created between the galaxies. The distances grow because the metric, the ruler, the measuring tape of the universe is stretching. And so the question that everybody asks, what is the universe expanding into, doesn't quite make sense. It uses the wrong picture. It imagines the universe as a balloon inflating inside a room and asks about the room. But there is no room. Space isn't sitting inside some larger container. Space is all there is. When we say the universe is expanding, we mean that the distances between objects are increasing. That is the expansion. It's not expanding into anything. The thing itself is getting bigger. The question is like asking what's north of the North Pole. It feels like it should have an answer, but it doesn't, because the question misuses the concepts. All right, so the universe is expanding. Now let's do something fun. Let's run the movie backward. If galaxies are all moving apart right now, then yesterday they were a little closer together. Last year, closer still. 1,000,000 years ago, much closer. 1 billion years ago, crammed much tighter. Everything hotter, denser, more compressed. Keep rewinding. 2 billion years ago, 5 billion, 10 billion. The galaxies aren't even galaxies anymore, just a hot, glowing plasma of particles. Keep going. The entire observable universe, everything we can see, everything we can detect, all the matter, all the energy, compressed into a region smaller than a grain of sand, smaller than an atom, a point of unimaginable density and temperature. That point, that moment, roughly 13.8 billion years ago, is what we call the Big Bang. Not a bang in space, not an explosion that happened somewhere within a pre-existing emptiness. The bang was the beginning of space itself. the beginning of time itself, the birth of the universe, including the arena in which the birth took place. I want to be careful here because the name Big Bang gives people a very wrong picture. They imagine a firecracker going off in a dark room. Stuff flies outward in all directions. There's a center where the firecracker was. There's an expanding edge, a shock wave, a boundary. Everything about that picture is wrong. There was no room. There was no center. There was no pre-existing darkness for the explosion to happen in. The Big Bang did not happen at a place in space. It happened everywhere. It was the event that created space. Every point in the universe was the Big Bang. Every location was ground zero. And asking what happened before the Big Bang is, in our current understanding, a bit like asking what's south of the South Pole. You've run out of the thing the question is about. But, now you might ask, how do we actually know the Big Bang happened? Maybe the universe is expanding right now, fine, but how can we be sure it was ever in that impossibly hot, dense state? Fair question. And the answer is one of the most satisfying detective stories in all of physics. In 1964, two engineers at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to calibrate a large horn-shaped radio antenna. They were picking up a faint hiss, a weak microwave signal coming from every direction in the sky. They couldn't eliminate it. They cleaned the antenna. They checked every cable and connection. They even chased out a pair of pigeons that had been nesting inside the horn and carefully scrubbed away everything the pigeons had left behind. The hiss remained. It was coming from everywhere, day and night, summer and winter, no matter where they aimed the antenna. Uniform, isotropic, relentless. They had stumbled onto the cosmic microwave background radiation, the afterglow of the Big Bang itself. Here's what happened. When the universe was very young, about 380,000 years after the beginning, it had finally cooled enough for electrons to combine with protons to form neutral hydrogen atoms. Before that moment, the universe was a blinding hot plasma, opaque like the thickest fog you've ever seen, with photons of light bouncing off free electrons, unable to travel more than a short distance in any direction. The moment atoms formed, the fog lifted. Suddenly the photons were free. They streamed outward in every direction, carrying with them a snapshot of that moment, that instant when the universe became transparent. Those photons have been traveling through space ever since, for over 13 billion years. And as the universe expanded, their wavelengths stretched. What was once a searing glow, hotter than the surface of any star, has been redshifted all the way down into faint microwaves, a whisper of warmth just a few degrees above absolute zero, and it's still here, still arriving, from every direction. A baby picture of the universe, written in light. Penzias and Wilson won the Nobel Prize for that discovery.